שלום, שלום.
היי, מה קורה?
מה המצב? טוב שהיה.
טוב שהיה? טוב שנגמר או טוב שהיה?
תשמע.
יש הרבה חברים או?
כן, כאילו כל הצוות המשך. מי שהצליח להתחנק, אבל תשמע, מחזירים אותך.
כן, מה? תחושה של טירונית כאילו?
זה היה קר. אז בסוף אתה...
זה היה קר? ישנתם בחוץ?
לא, קו כאילו...
היה קו.
כן.
כן, כן.
זה תופס קו.
כן.
כל מה שמשתמע.
כן, כן.
בן אדם... בוא נגיד שאני הכי אהבתי את הש"ג.
וואלה.
אתה עושה ש"ג, אין לך בעיות, אין לך... לא... נגיד, הדילמות המוסריות שאתה נתקל בהן הן הכי סבירות, כן. כאילו בתור תורן מטבח אתה נתקל ביותר דילמות. מה עדיף, להשקיע בשטיפה או לעשות את זה מהר?
כן.
כן, פשוט הזכיר לי שעבר קצת זמן מאז שהייתי חייל
וטוב שכך.
וטוב שכך, ממש. זה גם משהו שהייתי צריך לעבור.
אחרי זה צריך... בעיה. בעיה כזה. טוב, טיפשות. מה קורה? בסדר, יכול להיות.
מעולה, מעולה.
אהלן, נמצא. ואני אתחיל so last time there was something that I said that was not accurate, and Alon had a nice sketch. He told me, so maybe I'll just remind it. Last time so we call given phi from A to B of H completely positive. We call I don't know. Okay, did I denote it with subscript 5? Probably yes. K phi, pi phi, V phi, Stein spring relation. Stein spring relation of phi if everything, if phi goes from A. Sorry, no, that's right. Phi goes from A to B of K phi is star rep. And phi of A is and V phi is an isometry. V phi, and not isometry, just about the operator in general from H K phi bounded with V squared equal to phi 1, and the point, and it is direction, and phi A is V phi star phi A phi. Okay, so that's the point. I mean, I don't want to write here the subscript phi. I want to say something just about S times string dilation, not D times string dilation or anything like that. So I'm deleting the subscripts. And in general, S times string dilation, did not be minimal. Not be minimal. What is minimal? It's called minimal. It's called the minimal times string dilation if pi, if the span closure of pi a v h is k. Okay, so usually it will not be minimal. Unlike a GNS dilation, which is always minimal because psi is a cyclic vector by definition. And I'm just and the Stein spring dilation we constructed last time is indeed minimal. So the Stein spring dilation we constructed last time was the one that I usually denote as K phi, pi phi, V phi. Okay. This is a specific one, and this was minimal. And maybe I said something last time which was inaccurate, so now I want you to write it correctly. Okay. But in general, the Stein spring dilation is not minimal, but there are minimal ones and constructed ones. And usually, if I give you a Stein spring dilation which is not minimal, I can turn it into a minimal one just by doing what I wrote last time, which is, right, I define just, well, we squeezed everything. I mean, it was easy to this subspace. Okay?
Okay. We know that if phi is unital and H is one-dimensional, then V is an isometry, right?
Even if phi is unital, then V is an isometry.
Only if it's unital?
Yes.
Okay.
Okay, just, I mean, you see from here, if phi is unital, if phi of 1 is 1, then pi of 1
is also 1?
Then
this is my question, basically.
the answer is yes, but I just want to see if you see from here. So okay, I'll think about it. But the answer is yes. I mean, just keep trying. Okay. I mean, UCPs are compressions of unital star representations. Okay, this is my yeah. So so exactly. So the answer is yes if it's a minimal Stein spring representation. Exactly. So you cannot see it for me. You need to know it's minimal, right? Because I can always dilate it, you know, in a trivial way, like adding zeros, and then pi of 1 is always a projection because pi is a star representation, so it must be a projection. But it's not just a projection; it's a projection that שולט על כל התמונה של pi a כאן, right? For any element, I can write any element a as 1a1. Thus, pi of a is less than PAP, P pi a p, if p is the projection. So it's like, okay, I can, so if pi may not be unital in a general time string representation, but then it's just a corner. But when you make it minimal, then it will be unital. Okay. Good. So, and then we started to, and we said that, okay, now that we're done with time string dilation theorem, we can turn to Haussen's extension theorem. I'll remind you what is Haussen's extension theorem. Later we will prove it. Haussen's extension theorem, is just to say that if S is inside A, containing one of A, is an operator system, phi from S to B of H, a completely positive map, then there is a psi from A to B of H, completely positive, extending phi. So it's a sort of an Banach theorem. By the way, there is one case that we already know of this theorem, the case that H is equal to
C.
Why? Why do we know it for H equal to C? Right, note, if H is C, we already know it. It is just so we have a CP map phi from S to C, right? Because B of C is C. This is just a positive map. Then phi of one. Then 1 over phi of 1, which is scalar, times phi. Well, unless phi is 0. If phi is 0, it's trivial. If phi is not 0, I can always consider this map. What can I say about this map? It's a contractive, it's a positive map, it's contractive, it's unital, right? But in particular, it is a contractive unital. So I can, by the usual Banach, I can extend it to A. By the usual Banach, there is F from A to C, extending this. Take so F is contractive. I'm sorry, by the Banach there exists F contractive, and it also will also be unital because the original map is unital and this is just an extension. So if this is a unital contractive map, it is a state, and we know that states are positive, in particular completely positive, right? So phi is CP, so F is CP. F is CP as a state. So I don't know. So let's take psi to be right here, phi 1 times phi. Also CP. So okay, we know Haussen's extension theorem for the case that H is equal to C. What about the case that H is equal to C to the n?
Let's use Vn. Just the fact that phi is completely positive.
Again, the fact that phi is completely positive, what?
So let's talk about Vn.
Vn. And what do we know about Vn? Okay, we don't know yet anything.
You have a correspondence.
But between what?
Between maps into Mn and
right. So this is what I wanted to remind now. So in the very end of last week, I presented the following correspondence. So the title is CP maps into MN, because I'm not going only to discuss about Albertson's extension theorem, I'm going to say something else, which is of its own importance. So we defined last time if phi was a map, linear map from S to Mn, linear, we defined the map f phi from Mn of S star into C to be like this: f phi of Aij was 1 over n ij phi iaj. This is an n by n matrix. I take its ij coordinate, and this is also equal to 1 over n ij. Right? The ij coordinate of a matrix is always ei phi aij ej, where ej is the standard basis. Right? This is just to absorb the ij coordinate of a matrix. And we can also, if we call E the vector E1 until En, which sits in C to the n square, then I can think of it as if it were 1 over n times E phi n of the matrix Aij E. So this is just a game. On the other end, if we start with an f, then we can construct phi of f. How? So phi of f of A, I'm going to give you the ijth coordinate of that, will be n times f of the following matrix. So write f lies now here.
Guy, did you mean like MNS to C or MNS star? Like last time
I wrote star because
yes, because you didn't want to write C.
I didn't want to write C. Okay. And so here it will be what? Go to the jth column and the ith row, right here Aij. And all the rest are zeros. Okay. So claim these are inverses of each other. And phi is unitar. If a number of f. That's the reason 1 over n sum would be otherwise. Okay, so this is an easy exercise, we can do it. Theorem that S an operator system A, phi from S to Mn linear, then the following are equivalent: 1 to A phi is completely positive, B, phi is n positive, C, F phi is positive. And I'm going to tell you the proof before I'm going to write it. The idea is like this. Okay, of course, A implies B and B implies C. Why B implies C is immediate. Why B implies C is immediate? Because
of this.
because of this. Do you see if phi is n positive, this matrix is an n by n matrix. So this, if phi n is positive, then this matrix is positive. And if you take a positive matrix and you do some vector, no matter what vector, in a product, positive matrix, another vector, it will be positive. So phi f will be positive. Okay. It's fine. So we have A implies B implies C. Are we going to show that C implies A? The idea is like this.
Another vector or the same vector? Should be the same vector or
What?
if
No, I'm saying it is true for any vector that I know psi, phi n, whatever, psi is positive, specifically to this vector. Now I'm saying how am I going to show that C implies B? If f psi is positive, then I can extend it from S to A like this. Like this Austin's extension theorem for the case H is equal to C, right? So it is just saying I can extend positive functionals to positive functionals, right? So I'm going to extend this map to A, and then I'm going to go in the reverse direction. So from this extension G, I will get phi G. And computation will show me that this should be the extension of no, yes, sorry, we're not proving Austin's extension yet. So okay, so it will be positive. This will be completely positive. So we will show easily that this guy will be completely positive on A. Therefore, its restriction to S is also completely positive, which will prove A. And on the way, for free, we will get the Austin's extension theorem for the case, for the finite dimensional case. So I will show you. Don't just go. Okay. Okay. So proof. Don't need to show. I think like that. Assume F5 is positive. And extend it to a positive inner functional G from M and A, right? To see F5 is from M and S to C. I'm extending it to this. And I will not do the computation. I mean, it's an easy computation. Let psi be phi of G. So psi just goes from A to Mn, right? Since G extends Fi, and the correspondence was 1-to-1, it's really easy to see that psi extends phi. So since G extends F, phi, easy to check, and psi, which is Fg, phi G extends phi. We'll show psi is completely positive. So to show that psi is completely positive, I have to do what I have to do. I have to show it is M positive for every M. Right, so we'll show it's M positive. So I need to check that psi M, right, that goes from M sub M of A to M sub M of Mn is positive, right? Now, recall that last time I gave you an exercise, which, by the way, I made a new exercise sheet. I will send it to you today or tomorrow, I think. And I wrote it there, that any positive element in this star algebra is of the form sums of M terms, each of the form like a rank 1 matrix, which is a AI star AJ. So from the exercise, it will be an exercise too, but also I gave it to you last time. Any positive matrix in MMA is an M sum. Can I say an M sum? I mean a sum of elements, an M sum of matrices, or sum of M matrices of M matrices of the form AI star AJ for A1 AJ AM in A. Okay. So to show that this is positive, it's enough for me to check it only on these matrices. So I need to show psi M of this matrix.
Right.
Can.
So again, now we assume F5 is positive, and you promised us to show that psi is N positive.
Now we're assuming that Fi is positive.
And you want to show that
I'm going to show
psi
that psi is completely positive
but you only said that it's M positive.
for everything. So yes,
sorry.
M is not N.
Can.
We'll show psi. Let me add here. Let M be some natural number. Okay.
Sorry.
I'm going to show it's M positive for everything. So, okay. So now, okay, so this matrix sits well. This sits in a, this is a matrix in M of Mn, right? So it acts over C to the mn, but I will take a vector x in C to the mn, and I will write it as psi1 until psi m. Each of the psi i's is in Cn. And I want also to write each psi I and write each psi I as lambda ik as a linear combination of the standard basis. And now I will do the computation, and you will see, I mean, there is a point here, but not a very big point, but okay. But the point is the following one. So, so I'm going to show that psi, how do you call it? Psi m of ai star aj is positive, okay? And then we're done. Right? Okay. So this is what? This is just let me write everything. This is psi1 until psi n. Psi m, sorry.
Psi is x.
No, these are the xi's.
Yeah, but the psi.
These xi's are x. Yes, I guess. So, and here we have this psi of a1 star a1, right? Until psi of a1 star a m, psi a m star a m, psi a 1, m star a m, psi 1. Second, right? So now you open everything and you get something that looks like, okay, I'll skip some computations, but trust me, I mean, this is very easy. This is EL psi of ai star aj. Okay. Let ai be the following matrix. So that's the trick more or less. Lambda I1 ai until lambda in ai, and then zeros elsewhere. This is a matrix in M and A. Then so recall that psi is nothing but f of g, psi of g, right? So therefore f of psi is just g. So g of the sum of all these ai star, sum of ai. So okay, this is a trick and nothing interesting here. This is g of ai star j, and sum over aj, and this is just ijk of lambda il, lambda jk, ai, a, j, and k. This thing. So this is this up to maybe n or something like this. So the positivity of this implies the positivity of that. So I'm done. Okay, I mean, yes, there is a game here with numbers. I mean, nothing.
What was G defined on?
So G was the extension of F phi. G was the idea is like this. Okay, maybe let me try to explain it in a few words. The idea is like this. We needed the C star algebra structure to do the proof. S is not a C star algebra, but I needed to multiply things. You see, I mean, I needed to multiply elements. I can do it in a C star algebra. So I lifted F phi from S to A. Now I have this linear functional in a C star algebra, right? Now it's just a computation. I mean, this is the now it is just an exercise in linear algebra. It has nothing to do with the C star algebras. I mean, it's an exercise about matrices to show that if G is positive, then its psi is positive, right? Then the correspondence psi is positive, and that's the exercise. I mean, this is an exercise. Like go home, do the details, and just an exercise. So okay, I wrote the details in. Maybe it was a mistake. So. Okay. But the main idea was that I can do the math in a C star algebra, not in a.
What if we would just stay in S? Like, I know that you're not supposed to multiply elements in S, but by our definition you can. And
What? How?
You by how we define the operator systems, you're allowed to multiply elements in S.
No.
You're not necessarily closed inside S, but you're allowed to multiply
But you
elements.
had to decompose the matrix into rank one.
So that was the lemma of the positives, that every positive element,
and
positive
the rank
matrix. That
one
was where.
matrices come from the C star.
Okay, so
Yes.
that's where.
Yes, keep in mind something like, I don't know, the operator system is something like the span of 1z bar as polynomials inside something very big, which is all continuous functions over the circle. I mean, you cannot multiply things, you cannot take square roots, you don't have all the power that you have in a C star algebra. So if you can extend things, if you can lift things to the C star algebra, then you can play.
Yeah.
So that's the point. Along the way,
Well, my question is not why do you need to lift? Can't you just play? You have this ambient system algebra, you can use it, that it exists, and play. And when you multiply things, maybe you're kind of like when you use complex numbers when you do real analysis. I mean,
okay,
like,
yes, you're right.
you
The point
use-
is that I needed to apply the functions on. So you're right. Maybe I could do the proof inside, I don't know, S times S.
S times S. Yeah, exactly.
Okay. Maybe the
Yeah.
proof, well, I mean, maybe the only thing I need for this proof is to
Multiply.
extend it from the word of S to the word of S times S.
But you still need to.
I think this is right. I mean, I think I never took a product of more than 2 elements, I think. So,
No, but I mean, these AIs, you found them, like you have control on these AIs such that these matrices would land in S.
But would you care that the AIs are inside S or not? Like you use.
to apply psi to them.
yeah.
Yeah.
Can I make them sit in S? No, that's right.
Okay.
So, I mean, okay, when I say no, I mean no in a deeper sense. I mean no, the positive, S has a lot of positive, S has many positive elements. I don't think that it has enough positive elements to know this kind of positivity. So I think it does need to have the positive cone of the C star algebra. But right, this is a very good question. Yes, okay, maybe. But I don't, well, maybe S times S doesn't, I don't know.
Maybe you can take the complexification of S in some.
But that's exactly, this is exactly the point. We don't care. And we don't care because we can lift it as much as we want. And that's the way I want to go. I mean, that's exactly the point. So, okay, so we also showed, right, along the way, along the lines, we showed Albertson's extension theorem for the case that B of H is Mn, right? Because A implies B implies C implies A. And in C implies A, we showed that we constructed a lift psi of phi, which was CP. So we did prove this theorem just as a corollary of the proof of another theorem. So let me write this. A corollary from proof from the proof. Albertson's extension. H is equal to TBN. If S is this top system, phi S to Mn CP, then there is psi from A to M extending. Okay. So now we want to go for the full theorem. By the way, I also want you to have in mind something. I present Albertson's extension theorem as if it is just an extension from an operator system into a sister algebra. But it's also an extension theorem from an operator system to another operator system, right? I mean, if there was another T, I mean, if we're in this situation, right, that I have a map, CP map, and here there is a T, which is another operator system, then of course T sits inside some A, and I can lift the map to here. So of course I can lift it also to T, right? So I stated that I'm stating the theorem about sister algebras. I don't know why. I mean, that's the way Albertson's like it, but it tells us something else. It tells us that whenever you have an operator system inside operator system, inside another operator system, you can always lift the map, you can always extend the map. Specifically if it's a system. Okay. Okay, so the proof of the infinite dimensional case is going to use the finite dimensional case. And somehow we're going to need a topology on the CP maps themselves. Okay? So for that, we will need to work a little bit.
How? I mean, say I take a finite subset in S.
Yes.
And I look at its image in BH.
Yes.
Is there any reason that this will be contained in some isomorphic to Mn? Like,
Say it again, sorry.
I kind of want to say, okay, maybe I can't see how to lift it on all of S. I only look at some finite subset of S, and I look at its image in BH. It's a finite set of elements, but now I want to say that it lives in some Mn, so I can use.
No, so that's exactly the point. I mean, so the example you should have in mind always, more or less, is the following one. S is just the span of one z bar. Okay. This is a very, the span of it, of course, but this is a very finite dimensional set. It's spanned by 3 elements,
right?
One z and z bar. And now I want to think of phi as a map that goes to that just embed them inside I don't know, C of T, which sits inside B of L2 with respect to the advantage.
And they span it then subalgebra.
So if you want to lift it to the sister algebra, so my point is like, Of course, this is finite dimensional. But the question is, what is the image of what we're looking for is not going to be finite dimensional. That's the point. It's not that this, if this were a star homomorphism, you're right. I mean, you start with something finite dimensional. The image is a finite dimensional sister algebra. Finite dimensional sister algebra lives inside Mn of something, but that's not the case somehow. Exactly because the way you should think about CP maps are as compressions of things that need not be finite dimensional. They can be infinite dimensionals, even when all you care about is the finite dimensional case. Okay.
Why this S is finite dimensional?
No, I'm just saying span of 3 elements.
No, but you can look on the multiplicity of Z, right? Z squared and
Right.
Z bar squared.
Right, but a operator system is not an algebra. That's the point. That's the point. The algebra they generate is infinite dimensional.
Mhm.
But as an operator system, it's just 3 dimensional.
If we look at the same theorem, but I want to work instead of with operator systems, or like I work in the category of sister algebras with star homomorphisms. Is this still true? Can you always extend star homomorphisms?
So Michael asks, let me give you an easier question. Suppose you're in the situation where, in this situation, that H is equal to C. So you have your C, and you have your sister algebra A, and it sits as a subalgebra of sister algebra B, and this is star homomorphism, so it is a multiplicative linear functional. Can I extend it here? So think about it. Even I want to answer it in many levels. Okay, I can give you an easy example, but I don't also want just to give you an easy example for A that sits in B. I can put there are many simple sister algebras in the world. Sister algebras without closed ideals. So B can be such. And then I can take A even to be, I know, C, and this map to be the identity map. And I will not be able to, right? Okay. And if you want a proper example, then let's take this C and take this to be M2 and send A here to A00.
You only get the UCP lift, which is on trace.
Right. Like Alson's extension does give me a UCP lift, a UCP extension, but this can never be star homomorphism because from M2 I don't have star homomorphism to C because it's simple. Okay. Good. So now and I showed it with C, but now that we showed it with C, we can show that it is true for any unitary sister algebra. That's right. Okay. So we said that we're going to work out to get a topology, a good topology of CP maps. Okay. So let me start with a short discussion, a general discussion. If X and Y are Banach spaces, then I can always consider the set of linear transformations from bounded linear transformations from X to Y star. Y star is the dual space, of course. Bounded linear from X to Y star. And this is a Banach space. This is a Banach space. And we want to find a pre-dual. What I mean by pre-dual of it, namely a Banach space E, such that E star is this B of X, Y star. When I say is, I mean isometric isomorphic in the category of balance. Why? Once I find such an E, then it means that this is a dual space. So this is going to have a weak star topology. And then we like weak star topologies. Weak star topologies are החיים עצמם, right? Because we have בהנחלה הוא blue and okay.
It will just be bxy.
What?
Will it just be bxy?
Will it just be
Bxy.
bxy? You're saying that the pre-dual of bx comma y star is b of xy? No. Almost. I mean, it's very up to something. So
This is the ultra weak topology, right?
Which one?
there is no sister algebra here. I have Banach spaces. I'm not speaking about any sister or fundamental algebra. Okay, so I'm just speaking about two Banach spaces, and I want to find the pre-dual. Okay. So fix an x in x and y in y, and define so okay. Sorry, no, later I'm going to use okay, no, okay. Let me go to x and y. I'm not sure about the notation, maybe I will. That's fine. Okay, that's fine. X and y. Don't care right now. Define. I'm going to define something. I'm going to define a linear functional on this guy. So I'm going to take the dual of this guy. Let me maybe just explain something quick to have in mind. Whenever you want to find the pre-dual to a space, always look on the dual. You have to find it there, because the pre-dual always embeds in the double dual. So a pre-dual is always something that sits inside the dual with some restrictions. Maybe there are many pre-duals, by the way. You have examples in mind. So define this by x tensor y of L is going to be L applied on x. So L is here, right? L is an operator. I apply it on x, I get something in y star, I apply it on y, right? And that's a number. So altogether, I got a linear function. Now, just something to have in mind. I didn't use anything that has to do with tensor product. I mean, for those of you who are afraid from tensor product, I didn't do anything that has to do with tensor product. I defined something. I used this notation because it's very good thinking about them as tensor product, because it's linear in x, it's linear in y, right? If I replace x by x plus x prime, then everything. And if there is a scalar here, I can move it to here. So it behaves like tensor product. I mean, it's isomorphic. The set of all these guys, or the span, is isomorphic to the algebraic tensor product of x and y. So that makes sense. And know that x tensor y of L, this is a number, I can take its absolute value, is Lx of y by definition, which is less than or equal to L times x times y. Therefore, x tensor y is less than x y. Right? Good. But also we have it the other way around. If F is in Y star such that the norm of F is 1 and Fy is Y, I mean, it's not hard to choose such an F using the Hahn-Banach theorem. And set and L is defined on X over X norm to be F, and with L norm is equal to 1, then, so just, I'm just doing a Hahn-Banach few times, then the X tensor Y of L is nothing but the norm of this times the norms of that, which is exactly X tensor. But that is of norm 1. So this tells us that X tensor Y, it's less than or equal to, and also I can get it, so it's exactly. So it's a really nice. So what we did here so far, we started with 2 Banach spaces, and we constructed a very nice norm on their algebraic tensor product, if you want. Very nice norm in the sense that it satisfies this. So usually we call to such norms cross norms. So this is a cross norm on the tensor product, if you want, of X and Y. Lemma.
This is what's called nuclear.
The map, sometimes, I mean, depending on the context. The map phi from B of X, Y star to, so I didn't give it a name. Let me be consistent with myself. Did I give a name? No, I did. Okay, so before that, maybe. Let Z, this is going to be the good one. Z be the span closure with respect to this norm of all the X tensor Y. X and X. Right, fine. So this is a subset of BXY star. Lemma, as I promised. The map phi from BXY star to Z star given by phi of L of X tensor Y is X tensor Y of L is isometric isomorphism. I forgot my water bottle downstairs. Maybe do you want to have a break now or? So let's take a break now. Okay, we'll get it later, but they have 2 drinks.
לא סגרתי. אז
מישהו פונקציונלית זה להציב פונקציה של פונקציה.
למה יש כזה אל?
אני מניח שאפשר לבחור משהו לבד משחק.
אתה יכול לבחור... זה הנבנח פשוט, לא? אבל הנבנח זה פונקציונלי, מאין זה אופרטור. אין הנבנח לאופרטורים.
אבל כל אופרטור עם רנג סופי הוא סוף לא. כאילו כל עוד אתה בוחר פונקציונל רציף, אתה יכול כזה לשלוח כל פשוט לדבר.
סוף ממדי יש משלים...
כל סוף ממדי
יש משלים...
כן, אתה יכול...
סגור. לכל סאבספייס סוף ממדי יש משלים סגור. כן. זה אומר בכל...
כאילו לכל סאבספייס סוף ממדי במרחב בה אנחנו להיות הקלה. זה מה שאתה
כן.
כן. אבל אני אומר אפילו בלי קשר לתת, אפשר להשתמש בזה, כאילו זו אותה הוכחה. כאילו אתה פשוט צריך לבחור פונקציונל לינארי ואז ללכת לפיו לאורך הוקטור.
כן, זה אותו דבר.
זה F כזה בכלל אפשר לקחת את הזהות.
F קיים לפי הנבנח.
כן, זה לא יכול להיות. F זה פונקציונל.
F זה פונקציונל.
זה גם לא.
וכזה כמו L, בגלל שזה רק תנאים על מספר סופי של וקטורים, אתה יכול להשתמש גם בהנבנח כדי לבנות כזה.
אז זה מה שקורה. E זה פשוט מה שכתוב שם, נכון? bx, y star, star. זה מה שיהיה E.
אם היא קיים, הוא צריך להיות משוכן שם. כלומר, אתה לא יודע שהיא בכלל קיים.
הוא אומר שזה זה...
זהו, כאילו, זה ברור שהוא משוכן שם, נראה לי אבל שאנחנו מכוונים להיות, שזה יהיה בדיוק זה.
זה לא יהיה...
הוא אמר שזה...
Z?
כן.
כלומר, אם זה BXY סטאר, אז זה אתה, זה יכול לטעון שהמרחב, אז הוא רפלקסיבי.
יש פה איזשהו משהו לא טבעי, זה בדיוק הנקודה, אני חושב שבלי בחירת בסיס, אם זה היה נובע לחלוטין, אז היית יכול להוכיח את זה איכשהו בלי בחירת בסיס. ויש פה בחירת בסיס.
יכול להיות.
אבל כן, אולי יש איזושהי דרך מוסרית אחרת. תגידו, יש לי שאלה לשאול. האם אתם, כאילו פגשתם בטח קומפקטיפיקציה של מחקרים טופולוגיים, נכון? אתם כולם יודעים מה זה סטון של קומפקטיפיקיישן? לא? מה אתם חושבים? כל השאר איפה ראיתם את זה? בטופולוגיה?
כן, ראיתי מה? אני לא ראיתי את זה.
אנחנו עשינו את זה עם פילטרים.
זה די סטנדרטי.
אצלנו תמי ציגלר לא... כשעשיתי קורס בטופולוגיה.
עשיתי one point compactification?
בטח.
מה, ואז קלאסי, לפחות תרגיש בהשפן.
one point זה הרבה יותר קל
אני אומר, ואז רק חלק סולאשי.
האמת גם אצלנו זה תרגיל פייט. אם אתה עשית טופולוגיה?
לא, אני עברתי.
עם אסף.
אז כן, גם אני.
זה תרגיל בית עם פילטרים וזה, נכון?
למה עשינו את זה עם שחר?
עשינו שלושתנו עם שחר.
עשיתם טופולוגיה?
כן. עשינו, הוא עשה את זה בשילוב, ואז המתרגל נתן לנו לעשות את זה עם אולטרה פילטרים בתרגיל, והיה שם מלא טעויות, ואף אחד לא הצליח את זה.
אני לא עשיתי טופולוגיה, עשיתם מכוון מטרים טופולוגיה.
נכון, הוא רוצה עשינו לפתח סטון צ'כי עם אולטרה פילטרים,
זה לא היה
בטופולוגיה.
אני זוכר משהו.
היה איזה קטע, הוא כאילו רצה נעשה את הגרסה עם האולטרה פילטרים של סטון צ'ך. בתרגיל, הוא כתב את זה תרגיל וזה, והיה מלא כזה.
אז רגע, אתה גם עשית את זה
ואף אחד לא הצליח להבין מה הוא רוצה.
לא,
כל שבוע הוא עושה את זה מחדש בתרגיל, ואמר שעכשיו זה בסדר, וזה לא היה בסדר.
ויש עכשיו את הקומפקטיפיקציה הכי גדולה.
לא זוכר את זה.
נמשיך.
הוא שם את זה כל שבוע?
איזה 3 שבועות הוא שם את זה, אני חושב. זה היה בולבוס, זה לא היה...
אני חושב...
הייתי עמוס, אז לא היה לי.
כן, גם אני לא עשיתי את זה.
איך ראיתם על זה? סטון, S-T-O-N-E, בצ'ך זה C-E, C-H, ובעיקרון מעל ה-C הראשונה יש וויץ' קטן. הוא צ'כי.
סטון צ'כי פאבליק.
ובצ'כיה, סין גרשת עם וויץ' זה...
כן?
ושלא?
כן.
איך הם קוראים צ'כיה? ככה, כמו צ'ך?
כמו השם נראה לי,
אבל
כן.
עם סין עם וויץ'?
בטח כן.
כן, אני חושב שזה CH.
אני לא יודע.
S עם וויץ' זה רומני.
נכון, יש גם בקומולוגיה משהו, נכון? יש צ'ך קומולוגי, אבל זה H.
באמת?
צ'ך קומולוגי מסמנים אותו.
אין איזה משהו עם Z בכלל? לא,
זה צ'ך עצמו
כזה,
מסכן.
ככה כזה.
כן, זה סתם, זה כאילו וויץ' אחר.
כן, אבל זה אותו וויץ', כאילו.
במקרה נראה לי.
משהו כזה, לא? אני לא יודע, אבל...
לא, וויץ' זה קיים לא, ברומני?
אין את העוד Z שם איפשהו גם בצ'ך?
לא.
לא. למה מוכר לי שיש?
באנגלית קוראים זה CZ.
בגלל השם באנגלית, איך קוראים?
לא באנגלית.
לא, באנגלית איך אומרים צ'ך פאבליק?
אני חושב שבגרמנית יש שפות סלאביות שבהן CZ זה צ'ק. כאילו, באיזשהו ייעוד. פולנית אולי? פולנית בטח.
בהונגרית.
בהונגרית? בפולנית אני די בטוח.
נכון, יש שם את הזי הזה.
הונגרית זה לא סלאבי.
נכון, בפולנית הרבה פעמים רואים שמות עם זה, וזה הופך
הונגריה זה די סלאב.
לא
לא
סלאבי.
בדיוק.
לא, סליחה, הונגרית זה לא.
זה כמו, זה במשפחה עם פינית ועם עוד.
סטרטינה ושיטו
מה?
מהמאמר.
פין הונגרי.
פיני הונגרית, איזה עוד שפות? איזה עוד שפות?
יש איזה שלושת אלה וזה שפה של זה, לא יודע מה,
שיטו זה יהודי.
שזה הר כלשהו שם.
שם פחד זה יהודי.
באמת
של מי?
לא, סטרטינה ושיטו זה איזשהו מאמר שקראנו
נכון.
פעם ביחד. לא היה מישהו שם תוצאה של... אז ז'ידו אני חושב שהוא הונגרי או פולני או רומני, והוא כותב SZ, כאילו, הוגים את זה ז'י, אבל...
הונגרית, זה
זה אומר יהודי.
לא, ZS.
וזה
ZS. הונגרית זה ZS.
ZS. אז אולי זה ZS, כן.
SZ הונגרית זה פשוט.
איך אני בהונגרית שכן? דלת הונגרית?
סבתא שלי הונגרית. סבתא שלי וסבתא שלי הונגרית, סבתא שלי מדבר הונגרית.
הילדים של צחיק מדברים הונגרית.
אוקיי, בצ'כית זה בכלל צ'סקה. צ'כיה בהונגרית זה צ'סקה.
למה מדברים הונגרית? כי הוא נשוי יש לך את עופר?
טוב, שהוא היה בארץ.
הוא עכשיו הוא עדיין בארץ.
הוא חזר שוב?
נראה לי שכן, שהוא כמה ימים כבר בארץ.
הוא היה שבוע בנובמבר.
נראה לי, אני חושב שעכשיו הוא בארץ.
חזר?
כן.
גם רז פה?
כן.
טוב, בואו נתקתק את ההוכחה של זה, זה לא הוכחה מאוד מעניינת, אבל...
לא יודע, אי אפשר לדעת.
אבל מה בכל זאת נראה את הפרטים, כדי שנוכל להמשיך. בקיצר, אתה רק... אוקיי, let me go back to English, let's prove it. Just know that this tells us that they can think about my space as a dual space of Z. This is what exactly we wanted to show, right? Okay, so proof. I had a black marker, but now I don't know if it's mine. It's not. Let's try. So is it clear that phi is linear? Yes, it's clear. So linearity. Check. Check.
What you need to check is that it's well defined.
That it is well defined, that it is, I don't know, do you see all the others? That it is isometric, that it is...
No,
I mean, if it is
linearity
isometric,
is obvious, but it's hiding it that might not
I'm
be
going
well
to show
defined.
that it is isometric and well defined simultaneously. I mean, that's...
What do you mean by well defined?
I mean, you kind of define like this, they extend it linearly to everything. So, I mean, maybe some X tag tens or Y tag is a linear combination of some of these.
Right, so maybe second right zero is a linear combination of the others, right? That's right. But once you show it is isometric, then it comes automatically with being well defined somehow. And also that it is surjective. I mean, I need to show everything, more or less. Okay. So, if I'm okay, I'm not going to write. I'm going to show because it's going to be okay. Maybe let me write isometric plus well defined. Isometric plus well defined. So what I want you to check first is that what is the absolute value of a linear combination of these elements. Right? So this is what? This is by definition this, which is less than or equal to xi cancel y I times n. So I mean, okay. Sorry. I mean, I don't need to show it is well-defined. I'm sorry, Michael. Now
It is, we showed.
exactly. I mean, the map that I'm considering now is phi, not phi of L. Phi of L.
Phi is just in canonical embedding in the double dual. It's the restriction.
Okay, yeah. Sorry.
Yeah. So yes. I mean, I was confused too. But yeah. Okay. I mean, there's nothing not well defined here.
Right, it's just this evaluation on evaluation.
Yeah.
Phi L is defined on maybe there is a well defined here. I define it on the closure of the spec. I define it. Okay, there is a well defined part here, but not the well defined we're talking about. An easier well defined. The fact that it is that okay, I took care of these. I mean, I need to check that phi of L is indeed in Z star in the sense that it is well defined. So I need to see this defines something on Z star, but right now it seems that I defined it only on little tensorons or on some of them, of course. Of course, I mean extend it linearly. So it is defined only on the span. So I need to see that that it is indeed defined on the closure. In this sense, I need to show it is well defined and it follows from me. So phi of L is with norm less than L, but also we can get quality, so it will be an isometry.
I'm a bit confused.
Yes.
Okay, you have where does Z live? Z lives in the dual space of this domain, right?
Right.
You have BXY star.
That's right.
And for BXY star, you always have a map to its double dual, right? Which is given, like, give me a functional on this thing, evaluate it this way.
From what star?
If you get a map, what I'm trying to say is I want to think of phi for a second as a map from VXY star to
Yes.
VXY star and then two stars.
So
Like the canonical embedding in the double dual of the
So you're saying these, you're saying this Z star sits inside BXY star star star.
right.
Yes.
I'm saying that
That's right.
I mean you always have this map to the
This is this map.
yes, it's,
Isn't it the other way?
You're saying okay. I see your point.
it's not exactly this map, it's this map composed with restricting to Z. Right?
Well, what you want to say is that the image is.
Yes. So you're saying okay. So I think what you're saying is that they don't really need to prove isometric.
Isometric you might need to prove, but it's always defining a bounded it's always defining a function. It's defining a bounded functional on BXY star.
Yeah.
And thus just by restricting, you get a bounded functional on Z star.
That's right.
What you need to see is that it has the same norm.
Right. So yes. So this is okay. Thank you. So what you were saying is that even the easier part of what I call well-defined, I don't need to show. You're right.
Yes.
I agree. I thought that. Yeah. That's right. I mean, right.
Yeah,
So-
this isn't an inclusion, I think. It's a quotient. That's the point. Z
Yeah,
is
maybe, yes.
contained in BXY
Yes.
star.
That's right. That's
Z
right.
star is a
I
quotient.
didn't think
itself.
about it, I just thought of
That's right.
restricting.
That's right. But never mind. I mean, you don't need it. Okay, you don't need to think about it because anyway, I mean. Okay. זה לא חוסך לנו שום חישוב, אז כאילו. Okay, אפילו נגיד את זה briefly. And find an unit vector x such that L of x is up to some epsilon over 2. So I'm going to write now like a physicist proof or something like this for a second. Find okay, I cannot write it. is equal to 2. Find also y is equal to 1, such that Lx of y is up to epsilon over f equal to Lx, right? Then x tensor y, we checked it before. It is norm of x times norm of y, right? Which is 1. And phi L of x tensor y is up to epsilon L, because of the way we chose. So up to epsilon L, now take epsilon to be 0, and I mean take epsilon to 0. And
How can you find such x and y?
tell me.
Because it's the closure of because the
No, by definition of a norm, the norm of L is the supremum over all unit vectors of the norm of X. So there is we can approximate. Okay, now I want to show that it is surjective, and that's somehow the main part. Fix some f in z star, and for every x in x, let f sub x from y to b c to c, I mean to be linear functional defined by fx, f sub x of y is f of x tensor y. And let since f x y, okay, you see what I'm going to do. I'm going to find an element L sub f that will correspond to this f. So first I find this linear functional. Know that f x y is less than or equal to write the norm of f times the norm of x times the norm of y, because x tensor y is norm of x times norm of y. Therefore, fx is indeed in y star. It's a continuous linear functional, and so define L sub f to be of x to be fx. So L sub f is indeed a map from x to y star. And it is linear, and it is bounded. And bounded, why is it bounded? Since since LF of x is well, it's the norm of fx, which is less than the norm of f times the norm of x. So okay, so we just need to show that the phi of LF is thus LF is in here, and phi of LF of x tensor y is by definition x tensor y of LF, which is right, which is x, which is what? Which is LF of x, right? By how these guys work. On y, which is f sub x of y, which is f of x tensor y. So phi of LF is f. So it's all good. definition we call the weak star topology. The weak star topology, it defines it meaning Z. Z defines on BXY star the BW topology. BW for bounded weak. And why is this? Well, because I'm bounded weak. So lemma, let L lambda be a bounded, and it's important that it is a bounded net in BXY star, then L lambda goes to L in BW topology if and only if L lambda of X goes to Lx in the weak star topology of 1 for every X. And that's the origin of the name, more or less.
But it is the weak star topology on BXY star with respect to
With
this
respect to
particular
Z.
predual.
What?
With respect to this predual.
Yes,
There might
with
be
respect to
another
this
predual.
predual.
Yeah.
First of all, there might be many preduals.
Yeah.
It's not I didn't say anything about. And second of all, yes. And this agrees only on bounded nets. In general, this is not true. This,
And if X and Y were C-star algebras or von Neumann algebra, so this was the ultra weak topology. Then
okay, so I don't want to go over. So yes, okay. The point is that any von Neumann algebra has a unique predual. Once there is a unique predual here, then things are more. We can speak about the BW topology, which is sometimes called the ultra weak topology. But now we should be careful because I'm speaking just about Banach.
so the key point here is just the uniqueness of the.
I think so. I think so. Yes. I mean, we should. Not for this lemma.
Yeah.
Okay. Let's show. Okay. So proof if L lambda goes to L in the BW topology, let X be in X, then for every Y in Y, of course, we have that L lambda of X of Y, which is nothing but sorry for that.
Great, you're here back. Thanks.
We lost the charger. but now it's fine. So if anybody is going to watch this, I mean, it's going to be in a separate recording, but we're now in the middle of, or
You should say that in the
Last hour of
previous
the-
recording.
what?
You should say that in the previous
No,
recording.
in next one.
Ah, so in the previous you should say it would be okay.
Previous, they will, if they would finish it. Okay.
Guy, let me maybe ask you this. Just,
Yes.
okay, we constructed a pre-dual, which is nice, but if we wanted, we could have just said that for every x and, so will this, I'm asking, will what I say define the same word? For every x and y, x in x and y in y star,
Yes.
I want to look at like the value. Sorry, not x in, I take x in x and y in y, not in y star. And I look at the, okay, we had this linear functional, right? X tensor y.
Yes.
This defines a semi-norm on this bxy star, right?
Yes.
And you take the the usual locally convex topology that is generated by all these semi, right? Like
Which semi-norms?
just x tensor y. Like you take x in x and you take y in y star, and you want the topology such that all of these linear functions
I
may be
see, I
continuous. And
I
how-
think I mean, if it's the same thing, then it should be true in general, right? So you're asking something else. You're asking Guy. Suppose I have a space, a Banach space E, and I take all and for every element in E, I define the following semi-norm on E star, which is sorry, no, for any element in a, no, it's not the same thing. Okay, I mean, I think we can think about it. Yes, sure. Okay, so this goes, I mean, now I assume that I have a BW convergence, namely, it's converging the weak star topology of Z, so this converges right on these functionals to x, y, L, which is Lx of y, right? So right? So this tells me that this is a linear functional in y star. So it converges to this linear functional on y star on y's, namely in the weak star topology. Where did I use boundedness? I didn't, right? I didn't use boundedness, I think. I didn't use boundedness. Conversely, I think so. If I mean, you should check me. Maybe I think stupid things. But right now, I think I didn't use boundedness. Conversely, I will need to use boundedness, I think. So if for every x in x, I have this weak star to Lx, then this means that for every x in x and for every y in y, L lambda x of y converges as numbers to Lx of y, namely x tensor y of L lambda converges to x tensor y of L. And this will also be true for sums of these guys. Xi tensor yi of L lambda will converge, I mean finite sums, right? Converge to now, since L lambda is bounded, so if I have a bounded net that converges on a dense subset, then it will converge on everything. So since L lambda is bounded, then we do use boundedness for every z in z, z of L lambda. I know, maybe you should call it L lambda of z. Right, there is a duality here. It goes to L of z. So L lambda goes to L with M. Right? Okay. What now? So now, who is going to be my y? My y is going to be, well, I don't know, but y star is going to be B of h, right? We're going to speak about things that's with Albertson extension theorem. So I want y star to be B of h. So who is y? So that's the reason I gave you this exercise about the trace operators. And in this exercise, you show that so here I want y star to be B of h. In the exercise, I think it was exercise question 4, I think. We show that the trace class of H star is B of H. So B of H is a pre-dual, and in fact B of H is a unique pre-dual. I mean, it is a phenomenon algebra. Okay, we didn't give this term of phenomenon algebra to Sakai, but okay, I don't need it. I'm just telling you just for general knowledge. There is no other space that I can put here as y. It's only the trace class operator. In general, there might, but not in the case of B of H. And so remark B of H as any other phenomenon algebra as a unique pre-dual. But this requires a big theorem. It's not something. It's not that big, but it's not that small either. As a corollary, if X is Banach space and H is an Hilbert space, and then L lambda is bounded net in B of X, comma BH, then L lambda converges to L in the BW topology if and only if. Okay, of course I can write the same lemma of before. I can write if and only if L lambda of X converges to L lambda in the weak star topology, but you showed in the exercise that this is also equivalent to saying that L lambda of X converges in the what topology to L of X, in the weak operator topology. I did give you this in the exercise, right? I mean, I think the last item was to show that. Did I? That for bounded nets, the converging weak star and converging word is the same thing?
You're talking about BW topology. Isn't this just a definition? Like,
I mean, this is the lemma you just proved.
Not exactly. This is what? This is not weak star. This is the weak operator topology.
On BA, on BH. Wait, what are you talking about?
Okay. Look, guys. To say that these converge what to that is equivalent to what? So these guys are in B of H. So it means that for any psi, this is if and only if for every psi and eta in H, what is if and only? By definition, there is no theorem. By definition, this is if and only if for every psi and eta in H, L lambda of X of psi comma eta converges to this. This is by definition of weak operator topology. But these guys, you can think of them as rank 1 operators. So in particular, they are in the trace class. The trace class is a kind of a closure of the finite rank operators. I mean that's the reason I gave you this exercise. I wanted you to verify that you know that the trace class are closure in the trace mode of the finite rank operators. So and this is just a finite rank operator. I mean, you apply it on a vector. So okay, if you want, I can prove it. I mean, directly. I don't need. Okay, you know what? I can prove it. I mean, it's not a big proof, but I do want you to do it. So I will leave it as an exercise. Not because it's something I mean that will take too much time. It will take me 2 minutes, but I want you to do it. I want you to verify that you understand the notions. So please do it. Unless you immediately see it, and then that's fine. Okay. So now. And when you do it, please also, okay, no, you can use the lemmas. So notation. I mean, exercise, and let me just tell you, it follows from things you show. Things you show in question 4. Okay. So notations, some of them I will also use later in the course, some of them not, but let me write all of them. Let M be a subspace of a sister algebra A, and S an operator system, H a Hilbert space, P positive in view of H, then I define the following sets. B sub R of M V of H is the set of all L in bounded operator from M to B of H with norm less than R. CD this is the same thing, but just with completely bounded norm less than R. CPR. What is CPR? I mean, I know this whole form. CPR.
Complex projective space.
No.
No, to החייאה.
Yeah. What's the name of the בדיקת מטוש with the
PCR.
PCR. Okay. Yes, PCR and CPR. Okay. CPR. Is now I have CPR, no, but this goes from an operator system. And this is the same, I mean, L in B of S B of H, such that L is completely positive and L norm is less than R. And there's also this CP of S, B of H, P, which is the same thing, but for LCB and L of 1 is equal to B. And lastly, there is UCP from S to B of H that is just CP of S B of H with IH.
S is not the subspace of the C-star algebra that contains M, right?
I don't know, it is another subset of another system. No, I wanted to write, let M be an operator space, but I never defined an operator space. So an operator space is a subspace of the system. This is for operator spaces, and this is for operator systems. Maybe I should define once and for all. An operator space is the subspace of the system. But usually I don't, I mean. So it's a question. We could do all this part of the course on operator spaces, but somehow, I mean, it's more flexible to do it on operator systems. And if you need some fact on operator space, you can do something. I mean, we showed once that how can we lift maps? How can we lift, let's say, contractive maps or completely contractive maps from operator spaces into completely contractive maps on operator systems. Completely contractive maps on operator systems are exactly completely positive maps on operator systems. So somehow once you know how to deal with this category of operator systems and completely positive maps, you are also familiar, you also know everything you need to know about operator spaces, about subspaces and stuff. Okay, so theorem. Each of these sets is compact in the BW topology. Is it clear why I can say the BW topology in this case? I can say the BW topology because the BW topology in such sets comes from the choice of a pre-dual of B of H, and there is only one, like this, which is the trace class. But even if you don't know it, so we fixed this trace class, and then it's the BW topology with respect to this. But with this remark, you know that there is no other way to define this.
You're saying that the only non-canonical point in the construction before was that Y might have a lot of pre-duals.
Sure.
Y star might have.
Right.
That's the
right. Although I'm not saying that the whole thing might not have another pre-dual, right? Yeah. I mean, this is another story.
That's such an example.
Okay. So proof. I think, for example, this guy, we know it. Why this guy? And also this guy. Well, at least not this guy, maybe this guy. Why this guy is compact?
Just Banachal. No, wait.
So yes, we know.
Take a closed ball.
What?
We didn't take a closed.
Ah, no, I mean the closed. Sorry, of course. Sorry for that. All of the less than should be less than or equal to. Yeah. So why is this compact? This is compact because it is closed inside a compact ball. I mean, yes, this is just Banachal. Yeah, I thought about it more than okay, never mind. So BR of M B of H is closed is a closed ball. Is a closed ball in B of M B H and so in the BW topology. BW, the weak star. What about CBR? Need to show, so now I just need to show this is closed, right? Need to, I mean, this isn't, I mean, need to show this is closed in here. Because then it will be compact. So let L lambda be a net. Fortunately, it's going to be bounded in CBR NBH, converging to L. If Aij is an n by n matrix in Mn of n, and psi 1, psi n, and eta is eta 1 till eta n in H to the n. Then eta times ln of Aij of psi, I want to show that it is, I want to show that L is completely bounded, right? Because I want to show it is closed. It is the limit of, we'll do the computation, eta times L lambda n of Aij psi. But this is less than or equal to in absolute value. In absolute value. This is less than or equal to L lambda n times Aij of Aij times eta times psi. But L lambda r here. So therefore this is less than or equal to r times the norm of Aij times eta times psi. So if you are the limit of something that is less than something else, then you are yourself less than this thing. So, and this will show that Ln of Aij, I mean, this will show that Ln is less than R. But this is true for every n. For every n, so L simply not less. Right? And the rest are similar. The rest are similar. Questions about this?
Similar in the sense that you're proving that you can prove that CPR is a closed subset of BR.
Yes. So yes. So for example, if you plug in S instead of M, then you know it is compact because the operator system is a special operator space. So this is compact with S here. And now you just need to show that this is closed in here. So you just need to show that whenever I have a completely positive elements that converges to something, then the limit is also completely positive. And you do such a computation and it works. I mean, I think the very same computation, you just need to know how to read it will do the job.
Didn't we say completely positive and bounded is for the same also? Okay, maybe not unique.
Yes, so UCC and UCC are the same things for operator systems. So you're saying, so for example, this also, it will follow from here, but it will also follow from this. And maybe this also follows from me. Okay. There may be many ways out.
Yeah, so CBR and CP are all.
I mean, CB1 and yes, and okay, it's not CB1, but unital CB1 is the same thing as unital completely contraction, but completely bounded is as unital completely positive. And then we can figure out some of the, but I mean, it's also easy to do it directly. Anyway, I would like to go to the interesting stuff. So theorem. Albertson's extension theorem. I mean, the point is that we have where to. Okay, let me explain the point. The point is that we know, we proved somehow in our hands, Albertson's extension theorem for the finite dimensional case. Okay, so let me write it. Write S in A, 1A, phi from S to B of H, CP, then there is psi from A to B of H, CP, such that psi restricted to S is 5. We proved it for the case that H is finite dimensional. Now, what's going to be the proof now that we know that completely positive maps are compact? The proof is going to do something like this. It's going to look something like this. I'm going to take phi, I'm going to compress it to finite dimensional spaces.
By projections?
By projections from both sides. When you compress a UCP map, it will remain UCP. Or not UCP, CP, to remain CP. Completely positive. Then I'm going to run over all finite dimensional subspace of H. This is going to be a net. A net. So I know. Sorry, no. There is any finite dimensional compression like this I can lift because of the theorem we already proved. After lifting it, I'm going to run here. So in fact, I'm going to run here in the case that S is a sister algebra is A. And I'm going to find it's compact, so I have a limit. So I'm going to find such a limit, and then I'm going to show that this limit is in fact have to do a lift of the original map. So that's the idea of the proof.
Why did you say that UCP does not remain UCP if you compress it?
It does. It does. I didn't say.
No, the
No.
U, because of the U.
The U, yeah, it's not be unital anymore.
It is. I mean, into the image, into the.
Yeah.
Yes, but no. I mean, I'm writing the theorem for CPs. Of course, if this is UCP, then this would be UCP. But I'm giving it in more general sense. So proof. So now I'm just going to try to do it correctly. But that's it. So let F in H be finite dimensional subspace. Let phi f of A to be PF phi of A restricting to F. Well, pi f is the orthogonal projection. Like pi f is the projection, orthogonal projection onto F. Since so this is CP2, phi f is CP2, since BF is finite dimensional, right? It's n by n matrices where n is the dimension of F. And by Albertson's extension theorem for matrices, by Albertson's, or maybe let me just write by the matrix version, So we proved the matrix version using the one-dimensional version, right? And we prove now the infinite dimensional using the matrix version, and the one-dimensional case was not for free. I mean, it was difficult for us to show that states are right. If you think about it, we use the fact that linear contractions, that unital contractions are positive. This is something highly non-trivial that we proved in the first part of it.
We also used Anbach.
Also Anbanach, okay. So
I mean, no, it's not that even you proof of Anbach.
right, it's not, it does not give any sense in the proof. So by the matrix version, there is a CP extension, and let me call it psi f of this phi f. So psi f from A to B of f, right? Of phi f. Now, just something small, I want to think of these guys as sitting not inside B of f, but inside B of h. So let psi, I know, twiddle of f be psi f of a direct sum 0 on f perp, where I think of h as f plus f. And I just want to think of psi f as going from A to B of h, okay? Because I want to put them all in the same space. Now, capital curly F, which is all the finite dimensional H spaces, is directed under inclusion, so it gives us a net. So psi twiddle f sub f in f is a net in CP norm of phi of A B of H, which is compact. The latter set, which is compact. Hence, as a subnet, as a converging subnet, say to psi. We claim that psi does the job. I mean that psi itself is the extension. Let's see. If A is in S, and psi and eta are in H, let F naught to be the span of psi and eta. So this is a two-dimensional space. Then, so every F containing F naught, we have that eta, comma, phi A psi is A. Phi A psi is eta psi f with a psi, and since the set f curly f so before I say, okay, I just want to be very precise. So before it said subnet, let me give it a name. So psi f twiddle f in f curly prime. Now I'm taking curly f prime prime to be all the f in curly prime one, I mean in the subnet, such that they contain f naught. And no, I mean this is a cofinal net. I mean this defines a subnet. So if the subnet in f prime convergent, then this will be convergent.
I can extend. What do you mean then f naught is contained in f? Who is f here?
What?
You defined, you
That
started.
for every f containing, for every
okay.
f finite dimensional containing
Okay.
f naught,
Uh-huh.
This must agree.
Okay.
Because
It lives inside, yeah, of course.
because
This extends on finite dimensional.
Exactly. Yes. So now I take a subnet of my original of my subnet. I go only on spaces that containing this f naught. And this is a truly subnet. This is what I want to say. So what I want to say, and for this psi f twiddle f in f prime prime is a subnet. So what I'm just to try to say here is that to be a subnet means that for any element in the original, for any index, I can find something bigger that is in my subnet. I mean, of course, this is true for spaces that containing a fixed two-dimensional space. For any finite dimensional space, you'll be able to find somebody bigger that containing both of them. You can do this trick. So this is also a subnet, and eta psi a psi, which will be yes, it will be eta phi a psi.
It's not a problem that in the converging subnet you could have nothing containing f naught, or it must contain f naught.
No, so
What's the problem?
Itamar asks what happens if this f prime does not contain any subspace containing f naught.
No, it has to. Both are cofinal. F prime and F prime prime are both cofinal subsets.
Right. They're both cofinal in the sense that they define subnet. So it means that for any element here and for any element there, I can find somebody bigger than both. So it will be in both subnets, and therefore it cannot be the case.
Okay.
Right?
F prime intersection F double prime is also a final subset.
Yeah. F what?
F prime intersection.
Cofinal somehow means that you're from all the, I know it's cofinal in a linear order, but then I directed it means somehow from all directions
It just means that
you're big.
Yes, that for any two elements you can find yes.
Someone who's bigger than their join.
Yes.
Okay.
There is no join.
No,
For any element, there's an element.
Sorry, this is directed. Yes. So why do you want?
It just means that every element has, you can find something that which is bigger than.
Every
If you
element.
have
Okay.
cofinal, you
All
can just
elements,
do it
okay.
twice.
No.
Sorry, say it again.
You can take, like, if you want bigger than the join of x and y, you take x prime bigger than x, y prime bigger than y, you take their join. Then that's bigger than the join of x.
What?
Okay, I think it's okay. That's from what they say. It does. It contains any for any f. There'll be something there that is bigger than f in this subnet. So okay. So in particular for this F naught, you have someone who can. That's But when he says here subnet, is it still in the cofinal sense of all this, or it's only one direction?
No, I don't understand something else.
How do we know that F tag is cofinal?
So this is the definition of subnet from Etalon says that for compactness, it means that every net has a converging subnet. Turns out the meaning of this is probably of something.
Yeah, the meaning of this is cofinal. And again, what is cofinal you're saying?
So
every element has a bigger one.
But every element is a bigger one.
And it should be a directed set by itself.
And it should be direct.
but that's a definition of a net.
So
You're saying the
again,
cofinal
tell
subnet.
me
subnet,
why,
okay.
why do we have in F prime? Why do we have in F prime sets that contains F naught?
Exactly, because what they said is that it's any element in F,
Even F.
you have someone in F prime that is bigger than it, and bigger here is in containment. so-
Right. Thanks.
Okay.
Even
No,
much better, like F prime intersects F.
I mean, this is
prime.
cofinal. Okay, this is cofinal
This, yeah,
in
this-
F prime.
right.
Yes, exactly.
This is what I want. Sure.
Okay.
Okay, so
Its intersection with F prime is cofinal.
no, it defines in F prime.
Sorry.
I defined it in
Of
F prime,
course,
but okay.
Of course, sorry,
it could have been,
of course, yes.
could have been-
Yes.
Not fine, but it's fine. Okay, fine. So we're done. So now, good. So now, we showed that B of H has this property that we can lift, we can extend maps, CP maps or UCP maps from operator systems to other operator systems containing them. Now I want to isolate this property and to discuss about this. About this property of B of H, what?
Yes, finish the proof. Okay, so what?
The proof was what I promised. The proof was to take the limit from the finite dimensional case. Right?
Yeah, but what happened in the end?
You just
Can-
showed that the cluster point does the job.
Does the
Yes, I
job?
mean-
So you need to show that then.
I mean, this subnet converges to my original psi because it's a subnet of this subnet that converges to psi.
Okay.
So it must converge to psi.
And we know that it's.
And each element in this set satisfies this. So also the limit has to satisfy this, but the limit is psi.
And we're using the fact that we can look at the weak operator topology in this.
BW
Compact.
No, there is no weak operator topology.
What are those eta and psi's? Can you explain again? Okay, we constructed a.
No, I'm just saying to say that two operators are
The same
enough
it's
to
by
check the
evaluating
sign.
sign.
What I really want to show is that to show the two operators are the same, I just need to know what they do on finite dimensional space.
I see.
It's
Okay.
kind of.
Well,
No. If you know what they do on all finite dimensional spaces, then you're done.
Okay.
Would you say that this proof? No, never mind. I'll ask you.
So do you all know what a category is? So the title now is injective envelopes. So given a category, given the category C, definition. Given, no, before definition. Given a category C, definition. Sorry, definition. Given a category C and family of morphisms in C, or maybe let me call them H, this family. I will denote morphism of C like this, okay? More of C. And usually, I'm just saying, H will be certain monomorphisms. Is it okay that I'm talking in this language? I mean, if not, please interrupt me. Okay? Is it okay? So given a category C and the family of morphisms H in Mor C, an object I of C is called H injective if whenever I have a map, whenever I have to move two objects, X and Y, and the map that goes from X to Y and belongs to H, so this map belongs to the family H, and whenever I have any map from X to I, this is just any map, not any map in H. This is just any morphism. Then I can lift it to a map. Not in H, just a morphism. Okay, these are called H injective objects. These I's with these properties. Usually, in many books, so H is taken to be the class of all monomorphisms, but in other books, better ones, it is taken to be the class of all what is called regular monomorphisms. What are regular monomorphisms? So I'm not going to define it categorically speaking, but let me just say this. Whenever you have a monomorphism between X and Y, then in some categories, I can look on the image of X inside Y. And I need to have a sort of a notion of an image, of a map, not a range, an image like tmuna shel X inside Y. And suppose I can restrict my morphism, my monomorphism from X into its image. In many categories, this morphism is not an isomorphism. So this is something you show in many categories in topology. What is not an isomorphism? So suppose you are in a category in which you can restrict monomorphism to its image, to its image.
Right.
So
sometimes it's not an isomorphism.
Remark. Okay, let me write it while explaining it. Remark. When we are in a category that in which we can speak about images, about images of morphisms, i.e., if I have f that goes from X to Y, I can consider F as goes from, okay, what is this thing? And this is morphism, and this is a morphism. So, plus the latter is a morphism. Morphism. If F was monomorphism, the latter map, this one is sometimes, or many times, is generally not an isomorphism and isomorphism.
Are we talking about some like formal problem, like that we don't include it in the category, or that it's actually not a morphism, like the inverse is not a morphism or something like that?
So sometimes the inverse is not a morphism. Okay. And okay, now okay. First thing, sometimes I cannot do this. Sometimes, whenever I have a map, I cannot.
But that's like a formal problem. It's not like an actual problem.
Right, just a formal problem.
Yeah.
Now, suppose you do have this, now an actual problem. Sometimes it is not invertible. Sometimes it's not an isomorphism. Sometimes the one-to-one map does not give you an inverse from the image back because it's not a morphism anymore. You know it. I mean,
no, it gives
continuous.
I
I might have one-to-one continuous function from X to Y when X to Y are topological spaces, without having a continuous map that goes from the other way around. That when you compose them in both directions, you get identity. I mean, it's not invertible, right? I mean, this is a question in topology. Find two spaces X and Y, and a continuous map, one-to-one map from F from X to Y.
Bijection.
What?
And the bijection more than
In a bijection from X to Y that is continuous without a continuous inverse.
Yeah, so like the inverse is not a.
Yes, this is an actual problem. So I don't. What?
Can't you just assume the category is abelian? Or
Yes. I want to say something general now. Okay. I mean, okay. So I'm going to deal in categories that we do have this problem. That one-to-one monomorphisms are not embeddings. But now I want to consider the embedding. So F and monomorphism F and monomorphism F is called embedding if F from X to F of X is an isomorphism. And by the way, this notion of embeddings in general, I can also take it to categories where I don't have this problem, but I'm not going to. Then they are called regular monomorphisms. So okay, if you want, you can read about them. In general, we can speak about regular monomorphisms. These would be the embeddings in general, but okay, I will speak about the categories in which I can do this trick, and then I'll consider embeddings. When H is the class of all embeddings, H injectivity is simply called injectivity. Okay. So what's the point? Let me, I wrote too many words to say something very, very clear, very easy. I mean that I want to be in a situation where I can truly think about X as sitting inside Y. And the only thing I want to know, and I call it injective, if I can extend this map. Okay, but generally to speak about sitting inside can be tricky, but let's say it's not. Let's say we have embeddings in the sense that you are isomorphic to your image. So example, in the category of operator systems and UCPs, first, in the category of sister algebras and star homomorphisms, you're embedding if and only if you're star monomorphism. We showed that star monomorphisms, the images are sister algebras in an isometric way. So example not of H injectivity, just of what are embeddings. Embeddings in I don't know, unital sister algebras with star homomorphisms are all monomorphisms. Whenever they have a monomorphism, it is an embedding, right? So I mean, if I have a monomorphism from A into B, then A is isomorphic as a sister algebra into its image. Embeddings in operator systems with UCPs are what? So suppose I give you a map from S, which is UCP, and is 1-to-1 to T. So it is a monomorphism already. When do I have a I always have a linear map that goes the other way around because these are linear spaces. But when is the inverse UCP2?
UCC.
When it's unital completely contractive, you mean? No.
It's completely isometric.
When it's completely isometric. So this is an exercise. Then remembering if and only if. So here there is a statement, meaning that there is an inverse that is a UCP2, if and only if it is, if and only if they are are phi from A, if and only if phi is UCs. UCs meaning unital completely isometric. Completely isometric, meaning that all the phi ends are isometric. Okay. So you can think about it. I mean, just in a nutshell. I'm not going to do the proof, but UCP, you're UCP if and only if you're UCC. The opposite also needs to be UCC. Somehow, for these both to work, I need them to be unital completely isometric. I mean, if both of them will be contraction and not isometric, I'll have a problem. But you can prove it. I mean, it's not hard. It's an easy exercise. So, exercise. Okay. So that's the definition of injectivity, or of H injectivity, but from now on, I'll be interested in injectivity, where I have these embeddings. I will denote embedding. We will denote embeddings by hook terror, like this. So this does not mean monomorphism, this means an embedding. Now,
so Alvison extension is much more than saying that B of H is injective, right?
Why?
Because there you say that it tells you that any UCP to B of H could be extended, not only embeddings, not only unital completely isometric.
No. Wait, okay. Only this is embedding. So
Yeah. So
Again.
it's exactly. It says exactly.
it says exactly this.
Okay, sorry.
Only this map is in H. Only
Okay.
this one is
Yeah.
embedding.
Sure.
I really want to think about the case where you just lift maps to honest to God embeddings. So you can think of them as containments. You can think of X as a subset of Y. I mean,
Okay.
up to categorical isomorphism, that's the case.
Okay.
That's the point. So, okay. Okay, so I can erase it. So now I just want to give a bunch of examples and then we'll continue next time. And you see how important is this notion. Examples, in Banach spaces, over, I don't know, C or R, whatever you want, with linear transformations, transformations. We know that with injective. C is injective. Why?
And Banach.
This is just well, Banach in fact tells us that it preserves the norm, so I can write here linear contractive transformation. This is a bit stronger. This is just Han Banach. Han Banach, what Han Banach tells us? He tells us that whenever I have a map that goes from X to C, and X is contained in Y, right? And this is a continuous linear transformation, continuous. Oh, contractive. Linear transformation, then I can extend it, right? So C is injected. This is what Han Banach tells us. In operator systems with UCPs or CPs, whatever you want.
Do you know if there are other injective objects in Banach spaces?
Yes, I know.
There are.
Yeah. B of H is injective for every dot space H. This is what?
Alberson extension.
Alberson's extensions. In Unitel,
By the way, Guy, I meant actually to ask this back in the truth. When you don't use U, only CP,
yes,
Averson's extension theorem, like the way we proved it,
tells us that it preserves the norm as well.
it does preserve.
Yes, you're right. I maybe didn't write it.
Yeah, because it was important for the compactness, right?
Right, we saw it in the proof. I mean, nothing
Dimensional.
was important. We got it for free.
Sorry?
We got it for free. The fact that the psi had the norm.
But at some stage, like we needed to, we had to know it for the finite dimension. Right? Because these extensions, you want them to live in a bounded world. Take a link.
תודה, אתה לא צריך. לא, תודה. מה אומר שהוא לא להכין קפה פה? בעצם יש לנו מכונה למטה.
זה הסוד לשמור עליה הרבה שנים עובדת.
כן.
על מה?
זה הסוד לשמור עליה הרבה שנים עובדת. אוקיי, so you were saying that I needed all the psi to live in the so I needed to know that they are non-preserved.
That all these extensions have no.
Okay, I agree. So maybe Alon is right. Yes, I think Alon is right. And okay, in Averson's extension theorem, you can know that in all of the proofs we did, in fact, we could do it in a non-preserving way. I know that you can note it in the proof. I mean, it's easy. I noted this and I thought it's not important for what I'm going to need, which is UCP later on. That's correct. But Alon says that in the proof of Averson's extension theorem of the last version, I used the fact that I'm sitting inside a ball in the finite dimensional case which is bounded by some C, and I'm not sure, but maybe I did need to this fact from the finite dimensional case that I did all this extension in a preserving norm way. Okay, no, that's fine. I mean, you can. Anyway, yes, I'm going to here. In fact, yes, I care about this in this case. That's the structure. That's the right category. Well, units are commutative. C-star algebras and unital star homomorphisms, and C of X is injective if and only if X is what is called extremely disconnected. This is to say that closure of every open is open again. An example for that would be, well, any finite space. And a non-finite example would be Stonchak compactification of a discrete set. So an example of such, beta D for D discrete. Let me give you a quick, very cool definition of this Stonchak compactification of a set. L infinity of D is a C-star algebra. Verify this. I mean, we multiply functions, right? And it's commutative. F times G is G times F. So it has to be of the form continuous functions over something. Definition, call this something, this Gelfand spectrum, beta D. For those of you that are familiar with beta D, exercise, verify that the Gelfand spectrum is beta D. And this, well, this is I gave it one direction of this in the homework that I'm going to send you. So I think so if C of X is injective, I want you to show that X is extremely disconnected. The closure of any open set. And as we just said today, Michael asked me, in the category of unital C-star algebras with unital star homomorphisms, there are no injectives. There are no injectives. Right? We show that C itself is not injective, but if you think about it, this implies that nothing is injective. Let us play a little bit before going on. In groups with homomorphisms, only one is injective. Trivial group. Why?
It's true. Why only that one?
Why only one? I can give you a very quick proof of that. It's not trivial, but I think it's might be fun for this audience. So proof, if G is injective, well, regardless injectivity for a second, we can always take do you know what is the free group of two elements? Free group of two elements?
Oh, yeah.
I can always take the free group of two elements. Once I think of them as A, B, then I think of them as C, D, the elements, and I can construct a map that sends A to C and sends B to D inverse CD. And an exercise, this is one-to-one. If you want to prove it, I think one of the easiest ways to think about them as fundamental groups of, okay, think about it. Think about what?
Yeah, okay.
Okay, yeah, that's an exercise. And so if So if T is in my injective group G, or G, right? I don't know. G is in my injective group G. Let phi from A to B, AB to G, from F2 to G, send A to 1 and B to G. But then by injectivity of G, right, this sits inside CD using our map, using this map, which is 1-to-1, which is a monomorphism, it's embedding in this category. So then by injectivity, there is such a map phi twiddle. But this must fail. Oh, what happens? What is phi twiddle? Well, phi twiddle of C is phi of A, right? Which is 1, which is okay. But phi twiddle of D, no, let me check. Okay, let me do something else. Well, okay. What is phi of B? Phi of B is phi twiddle of D inverse CD, right? Which is phi twiddle of D inverse phi of C twiddle phi of D, but phi twiddle of C is 1. So this is 1. So, but phi of B is G. So G is 1. So I took an element in G and I showed it's 1. So G is the trivial group. And last example, and then we can really go on. And I will not prove it. In the category of abelian groups, this is also a nice exercise. A is injective. I will not put it in the exercise because it's not important for us. You can enjoy this. A is injective if and only if NA is equal to A for every N in A. Such groups are called divisible. So for example, I know Q, R, C, any field with characteristic 0. Any vector spaces, space over such.
What do you mean by NA?
Right. So abelian groups, in abelian groups, I can multiply elements by
You work by addition, okay.
right, I work by addition.
Okay.
So n times A just mean A plus.
Yeah.
Okay, n times. So groups in which I can do it for any natural elements, it's called divisible. And these are exactly the abelian groups. And I mean, I think a reasonable exercise, I think. But probably one direction is very easy, probably the other is not that easy. Anyway, see you next week. Bye, Hannah.